Good evening, all. My name is Pratyush Talreja, and I am one of the TAs in this course, Programming, Data Structures, and Algorithms using Python. And this is the week 7 of the course. So, for these week 7 lectures, Professor has covered the following topics, which are abstract data types, classes, objects, user defined lists, search trees. So, as we have already seen list in our previous lectures, in this lecture, we will be defining our own list. That is, we will be creating our linked list. And what is a linked list? So, in linked list or user defined list, we have two parts. One part is data, second part is the pointer, and that pointer points to the next node or null if that is the only node in the list. And then comes the search trees, which are binary search trees. We'll talk about this user defined list and search trees in the form of programming examples. So let's start. So this is the first program, which is write a program to perform various insertion and deletion on a linked list. So first we will see what a node in a linked list looks like. And then we will perform the following operations, that is insert element at the beginning of the list, insert element at the tail of the list, that is towards the end of the list, and then deleting an element with given data value. That means suppose if a list is 1, 2 and 3, and if we are providing 2 as the input to the function, then the output should be 1 and 3 because we have to delete the node with the value 2. So first let's start with what is a list, how a list looks like. So that will consist of a node, a class node. For this week, classes and objects are also covered. So we all know how to create a class. So in a class node, there will be a definition, which is a init function, which consists of two values, self and data. So this data will be equal to the value we are passing here, which is data. And then we declare a pointer, which will point to none, that is null at the very beginning. So let's see how this looks like. So let me go to paint and let me show you how this looks like, so that it becomes easier to visualize how a linked list looks like. So linked list consists of two parts. First part is the data, second is the value. Suppose the first data is 1. Suppose it is integer value 1. And suppose there is one more node in the linked list. Suppose the value here is 3, for example. So now this part is the pointer, which points to the next node in the linked list. And suppose this is the last element, suppose this 3 is the last element of the linked list. So here when it is not pointing to anything, we will say it is none, or we can represent it using x. That means this is the last element of a linked list. So now as we can see in this linked list, in this complete linked list, there are two nodes, and one node is having the value 1 and the second node is having the value 3. So let me write it here. This is the data that we have declared in our class definition, and this is the next node, that is the pointer, which points to the next node if there is a next node. If there is no next node, this will point to none, that is x. So let's go back to the definition. So this is a node which is having two parts, data and next. data will consist of some data. So every time, this is not the case that it will be integer only. It can consist of characters also. Like in place of 1, we can have A. In place of 3, we can have B. So there can be characters also as well as other integers also. So other data types also. So now, as we have visualized what a node looks like, we will create a different class and we will call it LL. This stands for linked list. Now what happens here is, here also we will define the init block where we will make it to point to none. I'll let you know like why I am writing this. Before going into the depth, first we'll go to the first function. So first function is to add the elements to the linked list. So in our definition, in our program, what is the first requirement? That is, we have to insert element at the beginning of the list. Second is insert element at the tail of the list. So first we will see how to insert the element at the beginning of the list. So suppose if we are inserting 1, 2, 3, 4, 5, so the output for this should be 5, 4, 3, 2, 1. Reason being, the first element to be inserted is 1, and when we are inserting 2 at the beginning, so 2 will come before 1, and then when we are inserting 3 at the beginning, so 3 will come before 2. That's why when you are inserting 1, 2, 3, 4, 5 at the beginning, output should be 5, 4, 3, 2, 1. So we will see how this works. First, let us write the function. So now we will define a function called as add front. And here also we will pass data. Now initially, one more thing is, while working with linked list or while working with any data structures, we should take care of the corner cases. And what corner cases are? For example, in a linked list, corner cases will be, we have to check if linked list is null. If it is null, we have to add that node accordingly. If it is not null, then there will be a different logic to add node. So first, what we will do, we will check if self.head is none. That means when you are adding the first element, linked list will be empty, definitely. There will be no node. When this is none, that means when linked list is empty, at that time what we will do, we will add the first element here. And how do we add it? We create a node, because we have created this node class here. And when you call this node and pass this data value, a node will be created. That means this node will be created, or we can say this node will be created, because for the very first time when you are creating a node, it will be having the data value and the pointer will be none at the very beginning. So now when this is none, we will create the node. Or else, for example, if linked list is not empty, that means we have to add the element at the beginning of the list. When this is not empty, at that time what we will do, we will create a new node. And then let me first write it and I'll explain what I am doing. So after writing this, let me explain you what these three things are. Suppose if linked list is not empty and we want to insert element at the beginning. So what we are trying to do, we are trying to create an empty node. Suppose we are passing node of 3. So in this case, consider this is temp, because temp is pointing here. Just to save time, I'll write T here, which is temp here. Now this node is created. This node is already created. Now what we want to do, so head is pointing here. self.head. Self.head is already pointing here because we have already added the first element. And now when we are adding the second element, T is pointing here, the temp node is pointing here, but we want to insert this at the beginning. So in this list, what is happening? 3 should come in the beginning. So now what we are doing, let me explain it here. Temp is creating a node 3. I will create it like this. And please assume that this 3 comma x is this particular node. So this is taking time to draw using my mouse pad. I'll write it directly here. So first, when you're creating a temp node, this looks like this. The first is data, second is a pointer. X means it is pointing to none. Now when we say temp.next, as of now temp.next is X, but we want it to point to self.head. So self.head will be pointing to the first node always. So self.head means first node of your linked list. Now what we are doing, we are pointing into self.head. So self.head will point to 1, for example. Suppose if the first element was 1. So when we say temp.next, so now this will point to the first element, that is head. Head was 1, for example. And then self.head will now point to temp. That means now self.head will point to this 3. So now what will happen? Here x will come, head will point to 3. So in this way we are inserting element at the beginning. Now again, suppose if you want to insert 2. So first thing will be, and this is our linked list. Self.head is now pointing to 3. This is the linked list. And now what happens here is, suppose you want to insert 2. First, on line number 13, you will create temp equal to node of data. That means 2 comma x will be created, a blank node. Then you are pointing temp dot next to self dot head. Self dot head is pointing to 3. That means this will point to 3. And then self dot head will point to temp because temp was already 2. So now self dot head will point to 2. That means now the list is 2, 3 and 1. Let us see if we are getting the output in the same manner. But now how to check the output? First what we do, we create a function to print the list. For that I will write the function print list, and here we will not pass any values because we just have to print the list. So we are not passing data here. Now what we do here, first we take a temp node, we point it to self.head because head will always point to the first node. Now after doing this, what we do, we check this while temp. That means while temp is not none. So what do we do at that time? We print the temp dot data value because we have to print the value. And when we use and equal to space here, that means when you print a new data in the list, the print statement will not go to the new line. That's why we are using this and equal to space. When you print the data, elements will be printed with spaces in between, with a single space in between. And now, so first temp is pointing to the head element and you are printing the value of temp. Now what you do, temp equal to temp dot next. So then when temp equal to temp dot next, this will check. If temp is not none, so second element will be printed. Similarly, when temp equal to temp dot next for the last node, this condition will be false because temp will be none here. And when this is none, this will not go inside. And in this way, we are printing the list. But now, first, we will create an object. So this was also covered in this week's lecture. So how to create an object. So what we will do, we will create an object named A, for example. A equal to, I'll do LL, that is the linked list. A linked list class which is created on line number 6. In this way, object is created. Now, how to call the function inside that particular class using the object? We use the dot notation. That is, if we want to call a dot front, if we want to call add front, then we will be using a dot front. Sorry, a dot add front, and f is capital here. And then we pass the value 1, for example. Similarly, I'll pass these values. After passing these values, what we do here is we just print the list. So as you all can see, we are adding 1, 2, 3, 4, 5, but every element is added at the front. So output should be 5, 4, 3, 2, 1. So we will see if we are going in the right direction or not. And how to print the list, how to call the print list? In the same manner, a dot print list, because a is the name of the object that we have created on line number 22. And to call the function inside the class, we have to use object dot function name, that is a dot print list. So now let us run the code. Now we have created the class node. Now we are creating the class linked list. We have created the object. And suppose we are adding these all together. Yeah. So now we have added a dot add front 1, 2, 3, 4, and 5. Now let us print the list. A dot print list. As you can all see, the output is 5, 4, 3, 2, 1. That means we have successfully added elements at the front of the list. So now let's move to the second sub problem. So second sub problem is insert element at the tail of the list. That means insert element at the end of the list. So for this also, we will create one more definition, one more function, or one more method. So we will create a method here and we will call it add tail. Here also we will do the same thing, self, and we'll pass the data. I'll explain you the logic for this also. But again, as I've already mentioned, that we have to check the corner cases. So what do we do here? We use the same thing. If self dot head is none. This is the case. If no element has been created, then what do? We just create the element. So for that, we create the element here only. I'll write it create node and the new element. If this is none, that means if the list is empty, because self dot head always points to the first node. And when we are saying if the first node is only none, then what do? We just create the element. So for that, what we will do, now self dot head will be pointed to the new node that is created on line number 17. And after this is done, we'll just return. We'll do nothing. Now, if this is the case when linked list is empty, but if the linked list is not empty, what do? We will again save the self dot head here. And what we are trying to do, we will traverse through the linked list. And we check while temp dot next. While next element is not null, then we do temp equal to temp dot next. And after this loop has been executed, we will write temp dot next equal to the new element, that is create node. And when you create the node on line number 17, it will consist of a data and a next pointer that points to none. That means that is the last node. But let me explain you what this function is doing, add tail. First, we are creating a new node on line number 17. On line number 18, we are checking if self.head is none. That means if the linked list is empty. If this is empty, this will always be the first node. So we do self.head equal to create node. That means the variable that we have created on line number 17, the node that we have created on line number 17. Then we do return. And then if this loop is not successful, we could have written this as an else block also, but that is not an issue. So what do we do here? We will use temp equal to self.head. Now we check while temp.next is not equal to null. So we do temp equal to temp.next, and then when this loop has been executed, temp will point to the last node. So what do we do? Temp.next equal to the new node, because we want to create element at the last. So let us do one thing. So we will do the same thing. We'll add this element at the front, 1, 2, 3, 4, 5, and we have seen that when we use a.printlist, this will print 5, 4, 3, 2, 1. Now what we will do, after this only, I will call a dot add tail, and I will add suppose 6 here. Again a dot add tail, I will add 7. I'll add 8. I'll only add 3 elements here now. Then I'll again do print list to show you the difference. Now again here what I'll do, I'll again copy paste this linked list class. Reason being, we have added one more function here. I'll do it for the class node also. It will not give me an error, but just to be on the safe side, I have again created the class node. I'm creating the class linked list here. Now when this is created, first we create the object. A is the object. Now we will add these 5 elements at the front. When this is done, we do a dot print list. And you can see 5, 4, 3, 2, 1 is printed. Now let's add element at the tail. That means towards the end of the list. So let me paste these 3 statements. After this is done, I'll do print list. So what should be the output of this complete list? The output should be 5, 4, 3, 2, 1, which was the original list, and then we are adding it to the end. That is, we are adding 6, 7, 8 to the end. So the output should be 5, 4, 3, 2, 1, 6, 7, 8. So as you can see, this is the desired output, and we have added 6, 7, 8 towards the end of the list. So in this way, we have completed two sub functions. That is, first function is to add, to insert the element, insert the data at the front of the list. Second is to insert the data, insert the element at the end of the list. Now let's check the third function, that is delete an element with a given data value. So what does this mean? Now as you can see, our linked list consists of these 8 elements, 5, 4, 3, 2, 1, 6, 7, 8. Now suppose if I am passing the value 2, so the node with the value 2 should be deleted. So that is our desired output. So that will be the node that is to be deleted, and the desired output will be 5, 4, 3, 1, 6, 7, 8, because we are deleting the node 2. So let us start by writing the function to delete the node. So for that I will call the function remove item or remove element or delete any element. Name can be anything. Again we have to pass data value here, because we have to make sure the node with that particular data value is deleted. Now we'll again do the same thing, but here what do? We start with a temp node that points to the self.head, because we have to traverse through the linked list, and while traversing only we will check if the element or if the data value is present in the linked list. If it is present, we will delete the linked list. We will delete the element in the linked list. Now again, as we have done for both of the functions, add front and add tail, we will do the same thing here. we will first check the corner cases. So first corner case is if self dot head is equal to none, or we can directly write is none also. So here, if this is none, that means if the linked list is empty, because when self dot head is pointing to none, that means linked list is empty. When the linked list is empty, what do? We will simply return. Why? Because when the linked list is empty, there is no node to delete. So we cannot delete anything from an empty linked list. That's why we are using this return, nothing else. Second is we can check if self dot head is not none, is not none, or we could have directly written else, because if self dot head is none, this will return, or we could have checked for else only. Now we have to check second corner case is if the list is not empty, we are checking it here if the list is not empty, and if self dot head, that is the first element, dot data equal to data. This data belongs to the data on line number 25, which we are passing from our code. So we check if the data is the first element in the linked list. That is also one of the corner case. So what do we do here? If this is the first node, then how to delete the first node? This is shown here. So what do we do? Self dot head. Now self dot head will point to the next node, and that is the reason why we are storing temp here for traversing and for again storing this value, because now we have to delete the first element. Now self dot head should point to next element. So what do we do here? We write self dot head equal to temp dot next, because temp is pointing to self dot head, that is the first element, and if first element is the element to be deleted, which we are checking on line number 30, we will use self dot head equal to temp dot next. That means now head will point to the second element, and by default head always points to the first element. Now if the linked list is 1 2 3, and if we want to delete 1, so head should point to 2, because in the new list, that is 2 3 will be the linked list, so 1 is deleted. So in this way we are deleting the first element in the linked list. And now when this is done, we do temp equal to none. That means this temp which was pointing to first node is now none. That means that node is deleted. And when this is done, again we will do return. After checking these two corner cases, these two conditions, now suppose if these two conditions are false, that means we have a complete linked list of n elements. So then how to delete elements? So sorry, how to delete n element, only single element with the value data. So for that we will traverse the linked list. And for traversing, as we have already seen in the print list function that we have created, we will use while temp. That means while temp is not none. So when this is done, now we check if temp dot data equal to data. If this is the case, we will do break. I'll explain why I'm writing this. And now we have to create one more pointer. Prev, that is the previous node. Previous node points to temp. Temp points to temp dot next. And after this while loop is done, we will do previous dot next equal to temp dot next, and temp will point to none. That means the temp element is deleted. So now let me tell you what this while loop is doing. I'll write it here only, then I'll delete. So now suppose the linked list is 1, 2, 3, 4, 5. Suppose we want to delete the element 3. So we call remove item of 3. What it will do temp equal to self dot head. That means temp is pointing to 1. I'll write like this. And we check if self dot head is none. That means we will check if the linked list is empty, which is not the case. So now we will check if self dot head is not none, and if self.head.data is equal to data. That means data is 3. If data is the first element of the linked list, this is also not true. Then we go to this while loop on line number 34. Here what do we do? Temp points to 1. So we check while temp is not empty. So now we check if temp.data equal to data. Now temp.data is 1 and our data to delete is 3. So this is also not true. So we are not going inside this if block. Now what do we do? We use this previous equal to temp. That means previous will also point to 1 because temp is pointing to 1. And on line number 38, we are doing temp equal to temp dot next. That means from this linked list, now temp will point to 2. So that's why I'm writing 2 here. Again, we will check while temp is not none, which is true, temp is not none. Again, we check if temp dot data equal to data, so 2 is not equal to 3. That means we will not go inside this if block. Again, now previous equal to temp. That means previous is pointing to 2. And on line number 38, temp equal to temp dot next. That means temp is pointing to 3. Now again we check while temp is not none, which is true. So we go inside. We check if temp dot data equal to data. So which is true. 3 is equal to 3. So we break this loop. That means we are breaking this while loop. After this while loop, after we have break this while loop, we will go to line number 39. That means previous next. That means 2 because previous is pointing to 2 and temp is pointing to 3. So previous next equal to temp next. That means the next of previous will now point to temps next. That is 2 will point to 4 because previous dot next is equal to temp dot next and temp equal to none. So that's why when we do temp equal to none, this will be deleted and the linked list will be 1, 2, 4 and 5. I hope the logic for removing an element from the linked list is clear. So let me remove this because this was just the explanation and this is the complete remove function. So now in the same way what we will do, we will first copy paste the code here. There was an indentation error. Let me check. Why is that? Okay, so there is no error now. Now let me copy paste this LL class, that is linked list class. This is also created. Now let's create an object. Let's add the element. I'll just copy paste the entire thing here. So this is what is the output. The current linked list is 54321 678. Suppose we want to delete 2. So what do we do? A dot remove item of 2. After this is done, we'll again do print list. And in print list, this 2 should be deleted and the output is 5431678. As you can see in this linked list, 2 was mentioned, 2 was present, and when we used a dot remove item of 2, then 2 is deleted. So this is the desired linked list. So this was the third function in our first program. Now before moving to second program, let us talk about the time complexity. So for the add front function, when we want to delete the element at the front, so what will be the time complexity there? If you think properly, what you are doing, you are adding the element at the first in the constant time, and that's why the time complexity will be order of 1 because you are not traversing the entire linked list, you are adding the element only at the front. So that's why the time complexity of this add front is order of 1. While you are writing any program, while you are writing any function, you should take care of this time complexity because for the small programs it is okay because your program will not take much time, but if you are writing very big program, which takes too much of processing, too much of computation, then this time complexity is very important. Now let's talk about the time complexity of add tail method. So in add tail, what you're doing, you're always inserting the element at the end of the list. That means you have to traverse the list to insert the element at the end, because when you are having the list, you just have the value of the head, that means the first node. So you are traversing the list always, that means the time complexity here is order of n, considering there are n elements in the linked list. And again, when we talk about the remove item, so is the item, if the item is at the front, that will be order of 1. But when we talk about remove item, the worst case complexity will be again order of n, because the element can be at the end of the list also. So that's why the time complexity of this remove item function is order of n. Now again, one more thing in this remove function, suppose if the list is 1, 1, 2, 2, or 2, 3 only, and suppose you want to delete 1. So as per our code, only the first element 1 will be deleted. After deleting 1, the output will be 1, 2, and 3. But just as an homework example, just for you to all think of a logic, I would like to give you a homework example in which you have to delete the every occurrence of that element. That means if you are passing 1 as the input argument for the function, then you have to modify this remove item function so that it deletes every occurrence of the data element. So for the homework example, when you are passing 1 as the input to this remove item function, you have to make some changes here. You have to tweak this function, and the output of this function should be 2 and 3, because 1 is deleted. If 1 is coming 10 times also, then also that 1 should be deleted. If suppose there is this linked list that is 1, 1, 2, 2, 3. If you are passing 2 as the 2 as the input, so the output should be 1, 1, and 3. So this is just a homework example which will not be counted for the scoring, but it will be good if you try this. So after we are done with this, we'll now move to the second program, which is write a program to find the middle of a linked list using one traversal. So why I have written one traversal? Because the simple logic for this is you can traverse the linked list, and we have already seen how to traverse a linked list. And when you traverse a linked list, what you can do, you can count the number of nodes. That means for this linked list, when you're traversing, you will see this, there are 5 elements. Then what you can do, you can traverse the linked list only till count divided by 2. That means you will only reach till the middle of the linked list. But in that case, what you are doing, you are traversing twice. The first traversal is for counting the number of elements in the linked list, and second traversal is for reaching till the middle of the linked list to print that middle element. But now what we want to do here is we want to find the middle of a linked list only using one traversal. So for that, logic is using two pointers, in which one pointer will iterate a, a step at a time, and a second pointer will iterate two steps at a time. So for example, consider the analogy of climbing stairs. So if you want to climb, suppose there are 12 stairs, and suppose if you are climbing two steps at a time, then you will take 6 iteration, and if you are climbing one step at a time, you will take 12 iterations. So suppose we will traverse, we will take two functions, we will take two pointers. One will go two steps at a time, second will go one step at a time. So when that first loop, that is the fast pointer, when it reaches the end, the slow pointer will reach in the middle of the linked list. So we'll see the logic, we'll talk about the logic. So first what we will do, I'll use the same function. I'll use the same functions. Yes, I'll keep the same functions as it is, just to save time. What I'll do, I'll write that function here. So for that, what do we do? I'll write the function print the middle element or the middle item. So for this, we will not pass anything, we'll just use self. Now there will be two pointers, and both the pointers will be pointing to the first element only, first element of the linked list. So now what do we do here? First we will call slow pointer, which will point to the head element. Second we call fast pointer, which iterates two steps at a time. This will also point to head element. This will also point to the head, that means the first element of the linked list. Now what we do here is, first we check if self dot head is not none. We have to check that linked list is not empty. Only when the linked list is not empty, at that time only we can print the middle element. Now what do we do? We will create a loop, a while loop, which will be if fast is not none and if fast dot next is not none, because we have to check if both the nodes are not none, then only fast can go two steps at a time. So we do fast equal to fast dot next dot next. That means when we only do dot next, that means we are traversing through the next element. But when we use next dot next, at that time we are traversing through the we are traversing second element from the current element. That means two steps at a time when we are using next dot next. And slow pointer will go to slow dot next only. And after this is done, so outside this while loop we can write slow dot data as the output, which is the middle element. You can write here also like middle element is comma slow dot data. Now before printing the output, let me explain what this is doing. So suppose linked list is 1, 2, 3, 4, 5. So the output should be 3, right? Now initially slow will point to 1, fast will also point to 1. So we are checking if self dot head is not none, that means linked list is not empty, which is correct. So we traverse through this while loop. That is while fast is not none and fast dot next is also not none. Now what happens here is, if this is not none, fast will go to next dot next. That will fast will move to 3 and slow will move to only next element, which is slow dot next, as we can see on line number 47. Again we will check if fast is not none and fast dot next is also not none, which is also true. So now fast will go to next dot next, that is fast will go to 5 and slow will go to 3, because slow equal to slow dot next. Now we check fast is not none, which is true, and we have written AND condition, and we are checking fast dot next is not none, which is false, because 5 dot next is none. That's why we have written both the conditions here, fast is not none and fast dot next is also not none. So after writing these conditions, what we can find here is after fast has reached to the end of the list, fast is not none is true and the second statement is false. And the logic of true and false is always false, because this is the AND logic gate here, for example. Now when this was the case, so now this entire while loop is false, so we will come out of the loop and we will print middle element is slow dot data, which is it will print 3 as the output. So let's print the program first. Create this node. This is also created. Let's write only these five. So now as you can see, the linked list consists of five elements, that is 5, 4, 3, 2, 1. And now let's call the middle element, middle item function. So when you call a dot middle item, this will print middle element is 3. As you can see, from these five elements, the middle element is 3. So this is how you print the middle element of a linked list. So in this way, we have completed this second function also, second program also. Now let's move to the third program, which is write a program to reverse a linked list or reverse a list. So if the input is 1, 2, 3, 4, 5, the output should be 5, 4, 3, 2, 1. Now let's do one thing. I'll directly create a function here itself, which will be reverse. And here also we will not pass anything, only self, because this will be having the self dot head will be having the entire linked list. Now here also we have to take help of two pointers. Basically we will be using three pointers here. So first is previous is equal to none. Current points to the first element. I'll explain the logic here. First I'll write the code and then I'll explain the logic. We'll iterate through the while loop and we can write while current is not none. And if this is the case, we are creating a new pointer, that is next. That means the next element, we could have created temp also, not an issue. You can write current dot next equal to previous equal to current, and current equal to next. Let me explain you the logic. After this entire thing is done, after this while loop is done, what do we do? Self dot head equal to previous. Now I'll explain what is happening here. Suppose the linked list is 1, 2, 3, 4, 5. So we will use the same variable that we have created. That means previous is pointing to none on line number 50. Line number 51, current is pointing to self dot head. That is the first element, self dot head. And now what we are doing, iterating through the loop. While current is not none. So current is not none because current is pointing to the first element. What do we do? Next equal to current dot next. That means next will be 2 for the first iteration. On line number 54, current dot next is equal to previous. That means now current is not pointing to 2. Current dot next equal to previous means current is now pointing to none on line number 54. Then what do we do? We write previous equal to current. That means previous is pointing to 1 and current is pointing to next. That means this is the linked list, but current is now pointing to next, that is 2. Again we check while current is not none, which is true. What do we do? Next equal to current dot next. Current is now 2, current dot next is 3. That means next is 3 here. What do we do? Current dot next equal to previous. That means current is now pointing to 1 and 1 is pointing to none. So we will write current is now pointing to 1. And on line number 55, previous equal to current. Now previous is also pointing to 2 and current is pointing to next. That means now current is pointing to 3. Similarly, for the next iteration, it will be next equal to current dot next. That means it is 4. Next is 4. Current dot next equal to previous. That means current is pointing to previous. That is 2. So now the linked list is 3, 2, 1. and previous is pointing to current. That means previous is pointing to 3 and current is pointing to next. That is 4. Again for the fourth iteration, current is not none. Next equal to current dot next. So next will be 5. Current dot next equal to previous. That means current is pointing to previous. Previous is 3. So it will be 4, 3, 2, 1. And previous equal to current, that means this will be 4. Current equal to next, this is 5. For the last iteration, next equal to current dot next. Now current is pointing to 5, so current dot next is none. Current dot next equal to previous, that means 5 is pointing to 4. Previous equal to current, that is previous is 5. And current equal to next. Next is none, that means current is also none. Again we go to line number 52, while current is not none, but in this case current is none. So we come out of this while loop, and what do we do? This is the most important step. Self dot head equal to previous. That means head is now pointing to 5. So when we are writing this, head will now point to 5. So when you want to print this, so the output of 1, 2, 3, 4, 5 will be 5, 4, 3, 2, 1. This none will not be printed, but just to show that 1 is pointing to null or nothing, I have written none there. So this was the logic of this reverse function. So let's do the same thing again. I will copy paste these codes. I'll write the same thing. So now let us first print the list. Print list is 54321. This is the original list. 54321 is the original list. Now we want to reverse this. So for that we have created a function named reverse. So we will do a dot reverse. After this is done, we will do a dot print list. And now the output is 1, 2, 3, 4, 5. That means we have successfully written a function to reverse a linked list. I hope this is also clear. Now let's check the program. Now this is the program 4, which talks about binary search tree. So now the mistake from my side is this is a binary tree. I'll just write a binary tree here. The difference between binary tree and binary search tree is already taught to you. I'll also explain with the help of an example. So now write a program to find if a given array is same as the post order traversal, or to check. I've also missed it. Check word. So write a program to check if the given array is same as the post order traversal of a binary tree. So now input tree is given, input post array is given. Now we have to check if the post order of this tree is same as this given array. So now output of this is true. So first what we will do, we will see what this post order, in order and pre order are. Before that, let me copy this thing. I guess I can copy it, yes. So this is the tree 1, 2, 3, 4 and 5. So this is a binary tree. That means there are two nodes, left node and a right node. So one is in the, so there are basic concepts of a tree. So this one is known as the root of the tree. And then the left node of 1 is 2. Left node of 2 is 5. Right node of 2 is, sorry, left node of 2 is 4. Right node of 2 is 5. And right node of 1 is 3. Now, there are only three notations here, which is root, left and right. So now, to represent a tree, there are different notations. One is pre-order, one is post-order, one is in order. So now, when it is pre-order, that means root comes first. I'll tell you what I am talking about. So this is pre-order. Post-order means root will come at the last. That means left, right, and root. And in order means root will come in middle. Left, root, and right. So before going into the program, what I'll explain is, so for this tree, the pre-order will be, suppose 1 is the root element. So we are doing 1, we have to print the root element. We have to always print the root element. So what we are doing here is, so for this, it will be 1, left element is 2, right element is 3. Now this is the root. So we have to first print the root element, that is in the output 1 is printed and left and right, that means 2 and 3 are there, because left element of 1 is 2, left element of, sorry, right element of 1 is 3. So now we have to check for this left node first, because it is root, left and right. So for left node also, what will be the case? Root, left, right. That means this 2 is replaced by 2, 4 and 5. I'll write it here. So again, first we have to print the root element. So now the root element is 2. So that means 2 is printed here. This is, I am talking about only of the pre-order. So 2 can be deleted from here. Now again, the node to traverse is 4. So for 4, the pre-order traversal is 4 only, because left and right node are empty. As in the list, the right side element is empty for the last node. For the leaf nodes, so these are known as leaf nodes. 4, 5 and 3 are the leaf nodes because they are not having any children. That's why we have to just print 4 in the output. So 4 is deleted here. Then we have to print 5 in the output because there is no, and 5 is the leaf node. That's why. And at the last, we have to print 3. So this is the pre-order traversal. So now for in-order traversal, what do we do? So I'll write it here. 1, 2, 4, 5 and 3. Or post order, we'll talk about for post order first. So post order means left, right, root. That means here it will be 2, 3, 1. Left, right and root. But again, we have to talk about 2. So for 2 it will be 4, 5 and 2, because left node of 2 is 4, right node of 5 is, sorry, left node of 2 is 4, right node of 2 is 5. So we will write 4, 5, 2. And here what we are doing is, when we are reaching to 4, what do? We check for left and right node, which is not present. So we will print 4 as the first element and we delete it from this. Then we print 5 because 5 is also a leaf node. Then we delete it from here. Now we can print 2 because we have already traversed through 2. So this is the root element. That means left, right and root. So we will print 4, 5, 2. So now we print 2 here. Again, after traversing 2, we will go to the right node first, that is 3. And there are no left and right node for 3. That's why we will directly print 3 because 3 is the root element. Then again the last element is 1. So we will print 1 as the root element. So in this way, this is the post order traversal. Now for in order, that is left, root and right. So here what do we do? For this, left, root and right. So for 1, left, root and right will be 2, 1 and 3. Then we have to traverse through this 2 also. So for 2, it will be left, root and right means it will be 4, 2 and 5. So this way the output of this is 4, 2, 5, 1, 3. This is the in order traversal. So I hope this pre-order, post-order and in order are clear now. But for this, what we will do, we have to write a program. So for this again, we will use the same concepts of a linked list. So what do we do here is we will create class node, but unlike linked list which was having only one pointer, this will have two pointer, that is left and right. So what do? We define the function here in it, which will be self and key. As we are calling data in the linked nodes, in the linked list we call it as a data. For the tree we will call as a key. So the keys in this binary tree are 1, 2, 3, 4, 5, and this is binary tree. And one more thing was binary search tree, which was taught in this week's lecture, which means in binary search tree the left node of the root will always be less than the root. That means suppose 5 is there as the root node, the left node can be less than 5 only, and the right node will be greater than 5. So as we are talking about binary search tree, binary means only two node, left and right. So the left node for this 5 can be 3, for example. Right node can be 6 because it is greater than 5. And again, these left node will be elements less than 3, and right means greater than 3. So for this, less than 3 is 1 and greater than 3 is 4. So this is an example of binary search tree. So this was the difference between binary tree and binary search tree. Now let's get back to our program, which is to check if the post order traversal of our binary tree is same as the given input array. So now we will create the tree element. We will create the tree node. So tree node will be having, I'll call it as value, or we can call it data also, but I'll call it value. Value equal to key. Then self dot left is none. Self dot right is none. So we have to create two pointers here. Now we will not create the class of tree. I'll directly create the function of printing post order. So I'll write print post order. Post order, I will pass root as the element. So now for this, what do we do? Again, our program is to check if both the post order traversal of this tree and the given array are similar. But initially I'll talk only about printing the post order. So for post order, this is a recursive function. We check if root. That means if root is not null. So post order means left, right, and root. So what do we do here? We will call this in recursive way. We first call left element, we then call right element, and as I've already told, for pre-order, post-order, in-order, we print the root element. So I will print root dot val, because val is the variable that we have written here. If here we would have written data, self dot data. Here also we would have print root dot data. So now root dot val should be printed, and after this is done, the list will be printed. The pre-order, oh sorry, the post-order list will be printed. Now I will use and equal to this, or we'll keep it as it is, no issues. Now to create an element, what I'll do, root equal to node of 1. That means 1 is the node element. I'll be creating the same tree here. Now second will be root dot left will be node 2. Again root dot right will be node 3. As you can see from the above given diagram, root is 1, root left is 2, root right is 3. Now again we have to create 4 and 5 nodes also. For that it is root left left, root left right. That means 4 is root dot left dot left. This is the node with the value 4. The node with the value 5 is root dot left dot right. And after this is done, what we are doing, we are simply calling print post order. Now let us try running this program. We will see the post order traversal of this list, which should be 45231, as we have already discussed. Let's create this. Sorry. So this node is created with a val, left and right nodes. Now I'll simply write this function. Just to save time, I have not written it inside the class. So this is written. Now we will create the nodes. This is how we have created the node. Now when I call print post order, okay, the root, I missed passing the root element because this was asking for root element as the input parameter. And that is the error we are getting. Type error. Print post order missing one required positional argument, that was root. So now we have to pass root here. Then only it will print pre-order, post-order, and in order, whatever we desire for. But here we are passing root and calling print post-order function. So after we call this, you can see the output as 45231. As you can see here also 45231. This is the desired output, and this is the post order. Now, just as an extension to this problem, what we wanted here was to check if our post order traversal of this tree is equal to this given array. So the given array is 45231, and the output is also 45231. Let me print it here. Yeah, these two outputs are similar. That means we have to print true as the output or yes as the output. That means the post order traversal of this tree is equal to the given array. But for this, logic is very simple. In place of directly printing this value, I am just giving you a hint, and this is a homework exercise. This is a homework exercise for you. In spite of printing this value, the hint is save that value inside one of the array or list, and then compare it with input list or input array. If every element is matching, that means you have to print true, or else you have to print false. So this is how we work with list and trees. And I guess this was it for this week. For the next week, we will be talking about dynamic programming in detail. Thank you so much.